Okay, uh, this is number 11, a series of the class of the video about digital image processing. In this lecture or in this video, I would like to talk about a stereoscope or just shortly stereo imaging and talk about this. And we have two sections, one section with two cameras and one section with only one cameras and knowledge about the speed of the vehicle. Okay, record the mapping of the 3D scene onto an image plane is many to one mapping. Many, so we have many point which is mapped to only one point of the screen. And this is this transformation. That this image point does not uniquely determine the location corresponding of the word. So with only one point, we cannot find the missing depths. That is missing depths information. And this is stereoscopy, as I said, which is shortly stereo imaging technique. For instance, if we look at the figure 2.21, which is here, I mixed up. So here with this, we have two image number one, image number two, with the which they are aligned for x and y axis, and they have the same z axis. The distance is z is the same from the word point, but we have two images, x1 y1 and x2 y2, like a human being with two eyes, one eyes and left eyes and right eye, something like that. And this P is the length, the distance, which is baseline. I will tell you about this in next. Let's start here. In this figure, I will show the stereo image involves obtaining the separate image view of an object, a single point W with distance centered at the two lens in base slice B, I told you. The objective is to find the coordinate x, y, z. This is important is the missing depth, which is z. With this, we have two image, one image x1, y1, and another x2, y2 with two cameras. They are aligned, of course, and so on. They're differing only in the location of the origin, their origin, condition using a method in the practice. And recall that after the camera, word coordinate system have the brought into the coincidence, the xy plane of the image is aligned with xy plane. So they are aligned with the word coordinates. Under this assumption, z coordinates of w, the word point here, same as this, both in both camera, the same as the both camera. Exactly the same. Recall previously I told you about this in equation number 530, which is the path. If I want to tell you, it's here, but later I will tell you that the word coordinate x is the x coordinate, image coordinate over lambda focal distance multiplied by lambda minus z, which is the missing depth, the distance, the distance of the uh, point. X, Z indicate the first camera moved to the origin coordinate system. The second one is also the same, keeping the same. Instead, the second camera also, we have the same formula for the second camera. So for second camera, it is the world coordinate, large X is world coordinate X. The small x is the image coordinate X. And this is the another with another camera, X2 with the world coordinate, and with the same second camera is X2 with the same focal distance and Z. Of course, Z1 and Z2 are the same. But the only difference is because the separation of the two cameras is and the Z coordinate is the same, and just we have the separation is the baseline. As I told you, the separation is just by B, which is baseline between the lengths of two cameras. So X1 and X2 relation is X2, what we world camera X2, what we see in camera number 2, what we see in camera number 1, the world camera X2 and X1, just X1 plus baseline is X2 here. It aligned with the world camera. Just difference is the length distance, which is B baseline. And with these two, I will tell you about this. Simply in this figure, I can tell you more better here. Okay. Uh, so here in this figure 2.22, just we see the two cameras XY, which is X only image 1 and image 2. So it is X1, Y1, X2, Y1, X2, X2, Y2 small, and large X, of course, Z. This is Z, and there are only the difference is B baseline. And this is plane of the constant Z. This is origin of the world. Origin of the world, we suppose is here, for instance, then everything like this. And so we have the formula. One is the, as I told you here, I will tell you before also, this one and this one. This is in figure, this figure, 2.22, which is this one, this one. So Z2 equals Z1 is Z, and the other one is the X2. The baseline is just difference of the, as I told you, this one is important. X2 is X1 plus B. So substituting these two equation, 52 and 53 into 50, previously, I give you this one and this one. So we get this one, x2, which is x1 plus b, is x2 by lambda and lambda minus z. And then substituting the 54 to 55. and solving for z. So we don't need, so we're just solving for z. I mean, we want to like to find the z. So we have here two equation like this, and then we can solve for z. And just you don't need a large x1, which is the word coordinate. Just with respect to lambda, uh, focal distance, baseline B, and image 1 and image 2, x distance, x coordinate. So Z is this. This is very important formula here. Z is the lambda minus lambda B over x2 minus x1. So the important thing is to find the what we see from image 1, x1, and what we see with the coordinate in image coordinate x2, camera number 2, and the difference between these two x and lambda focal distance and baseline in the distance up to. There is, for instance, in human being is the distance between two eyes is b. So then what we look at with the right eye and what we can look with left eye, then you can guess the z, the missing distance, which is indicate the difference between the corresponding image corresponding to x1, x2, determine the baseline, the focal distance, or the calculating the z coordinate of the z. And this is very simple. So this is from this we can find the missing depths. And then for other x and y coordinate of the coordinate of the world, just we can use the previously I told you the formula for that. And the for instance, we can find a points on the image. For instance, the best is the prominent corners, and just to find that this is a point on the image. For instance, we can have the image point here, so we have to, for instance, one corner in the image. I will show you in next example. So by this way, you can see, you can calculate the missing depths. So once again, I show you in this that we have the stereo imaging, we have the W or coordinate, and x1, y1, small x2, y2 with two images, and then we have the camera coordinate, this one and this one, and the relation is this one, or with this, well, then you can find the missing depths as I told you, the z. Let me just tell you from the previous lecture, just I want to recall this one. Yes, this formula, if you know the z, then from the image, you can go find the coordinate x and y. This is the two important, I mean, the previous I told you in camera model. This was in camera model. I think the lecture number 10. Geometry of the image. So this was this. And other thing that I would like to tell you, this was about the stereoscope and stereo imaging. This was previous one. You can see the previous one and then this one, then you can remember everything. And so stereo needs two camera, like two eyes uh, for human being. For instance, you can guess the obstacle in front of you. And this is very important in robotics to have two cameras and then guess the how obstacle far from the robots. Especially this is important uh, for the I mean cars that guess the front car distance, avoiding the collision with the front car or any obstacle, and find the uh, if we find this missing depths. But in the car, usually we have a single camera. In this case, for single camera, if you have the velocity, the speed of the car, then you can find with single camera also you can find the missing depths. How I can show you one example here. Type of the camera distance, two camera. This is two camera distance that I told you, or single camera measurement, which is dynamic. That is static. This is dynamic. And for single camera, with single camera, we need the velocity, the speed of the vehicle, of the robot, or of the car. For instance, we have two cars here. I don't want to show you more this car because maybe of the something. Then if you have the length L here and L plus delta L, if you are nearer to the obstacle, then L is increased. As a camera move to the obstacle, the Z decreases and L increases by del dz and dl. So this is a single camera, and this is if we are going to be near to the next car, then this is dz reducing the z, but L, the length of 2 points in the front of car or any obstacle, become more larger dl. So in this case, the almost this angle BAC and DAC are similar, but are almost the same. So the ratio of L to Z is almost same to L plus DL over Z minus DZ. So this is minus, remember. If this approximation is accepted, with other also you can tell this that usually LDZ is minus ZDL, which is the Z is the minus LDZ with 2DL, which is the minus L derivative of Z with respect to time divided by derivative with the L with the time. So it is minus velocity. This is velocity, dz to dt is velocity, L, the distance, and the rate of the increasing of L, rate of increasing of L. So this is by I mean, any way you find with this approximation or other way of thinking, you can find that the z, the missing depths, if you know the velocity is related to the length divided by length of the 2 point on the object divided by the uh, rate of the change of the air. That is all. So if you know this equation, z is equal minus v, minus because we are getting nearer. So this rate is increasing, so this is decreasing, anyway, it's plus. So z, that's why we put here minus. So the L, so this is decreasing, this is increasing, that is minus. So this is velocity, this is the length, and this is the rate of the change. So and Z, the missing depths can be found. And this is dynamic with the control and signal processing. You can find with single camera, we can by control speed, we can find the missing depths and avoid the collision. To avoid the collision against the front car, we feedback the velocity of this to the signal processing and just make a brake to be activated and avoid missing. with single camera. That's all I wanted to tell about this lecture. And thank you very much. I stop here.